Welcome back. We'll continue with the discussion on the properties of discrete Fourier transform. And the last property that we shall learn is the convolution property. This is the most important property. Convolution property. Now what does this property say? This says the if y of n is defined as the convolution between x of n and h of n. If two sequences are convolved in time domain, then if you take the discrete time Fourier transform of y, discrete time Fourier transform of y, that is same as the discrete time Fourier transform of x of n convolved with h of n is simply the multiplication of x of omega and h of omega. What's x of omega? X of omega is the Fourier transform of the discrete time Fourier transform of x of n, and h of omega is the discrete time Fourier transform of h of n. Right. So this is the what does this say? I mean, if you take the discrete time Fourier transform of the convolution, it becomes simply the product of the discrete time Fourier transform. This is very important property of transform theory. So if two signals are convolved in time domain, they will be multiplied in the frequency domain. This is what the result says. This is very important result of and the most important property of this convolution, this transform theory. This is very important, and this is the beauty of transform theory. So let's start with y of n. So to prove this, we know y of n is x of n convolved with h of n, and taking the discrete time Fourier transform of this, that will be simply n from minus infinity to infinity y of n e to the power of minus j omega n. But y of n is the convolution between these two. So writing it like this. So this is the convolution, substituting y. So this is the convolution. Now, using the definition of convolution, this is simply summation k run from minus infinity to infinity x of n minus k, x of n minus k h of k, then e to the power of minus j omega n. All right. So this is how we write it. Now you can see this summation varies over k, this summation varies over n. So let me rearrange the summations. So first I will write the one that varies with respect to k, and you can see this summation is independent of k, so we can take h of k outside. Then we can write this summation as k running from minus infinity x of n minus k e to the power of k omega. Now you can see what is the second summation. This is simply the time shifting property of this discrete time Fourier transform, and you can prove it also here to use the property directly. So we can write it minus k running from minus infinity h of k. This is simply x of omega e to the power of minus j omega k. This is the time shifting property of discrete time Fourier transform. X of omega is independent of k. It will be independent of the summation. So we have h of k e to the power of k. Have a look at this summation. What is this? This is the discrete time Fourier transform of h of k. So it is h of omega. So the discrete time Fourier transform y of omega is x of omega h of. So this is very important property of this Fourier transform. So if the two sequences are multiplied in time domain, if you take the Fourier transform of these, the result, it will be simply the multiplication of the discrete time Fourier transform of the sequence. This is very important property of transform theory. All right. Now, the last important result that I want to show you without proof is the Farswell theorem. Farswell theorem, which is very, very important for communication people. This says if the Fourier transform, or the inverse Fourier transform of x of n is x of omega, or x of omega is x of n, then we can get the energy of the signal either from time domain or frequency domain by using this result, or we can also use the frequency domain expression. This is the energy of the signal actually. So we can calculate the energy either from the time domain using this expression or using the frequency domain expression. That's like this. Here we see we are using a summation because this is discrete time signal and x of omega is continuous function of omega. That's why we are using integration on the right hand side. All right, let me end this session here. So these are the properties of the discrete time Fourier transform. I hope you understood the concept. Please repeat and please solve the problems yourself. Now, one more property that, all right, I don't know the property number is minor. Please check it. This is called scaling in time. If you scale the scaling time, if you scale the signal in time domain. So, in other words, what does it mean? It means if the 3 times Fourier transform of x of omega, again, discrete time Fourier transform of a, sorry, not discrete time Fourier transform x of a is 1 by a, so in other words, if x of n, discrete time Fourier transform of x of n is x of omega, then discrete time Fourier transform of x a n means when you scale the time. When you scale the time, then the discrete time Fourier transform is simply 1 by a times x of omega by a. It's replacing omega by omega a. Wherever omega occurs, replace this by this. All right. Now, before I finish this, let me end this session here. In the next session, we'll solve some problems